This is problem 17-60. So not only are we going to have a spring with two blocks, and not only are we going to have a box sliding, but we're also going to have the second box sliding and at an angle. Okay, and then on top of that, we're going to ask some more interesting questions about the system in this problem. So let's take a look at it. The pair of blocks shown in the figure are released from rest when the spring is unstretched. The static and kinetic coefficients of friction are 0.3 and 0.2 respectively. For the ensuing motion, determine A, the maximum velocity of the blocks and the stretch in the spring at that position. Determine B, the maximum distance that the 10 kilogram block will slide down the inclined surface. And determine C, if the blocks will rebound from the position of part B. Okay, so that last one's pretty interesting, actually. Let's take a look at the math. All right, so let's just cut to the chase and let's go ahead and draw our free body diagrams for the blocks. So the 5 kilogram block is going to have a weight that is going to be 5 times 9.81. There's going to be a tension, which is going to be internal to the system, but still relevant. There is going to be a normal force, and there's going to be a frictional force, so friction of A, and then there's going to be the spring force. And they give us on the diagram the coefficient, the spring coefficient, which is going to be 1,000. And I'm going to introduce you to a new symbol that is also used in the book, is the lowercase delta. Okay. Also, sometimes it's called a Dirac. Then we have the 10 kilogram box. So it's an angle on the ramp. And there is, of course, a weight. So 10 kilograms times 9.81. There's going to be a tension internal to the system. There is going to be a normal force at an angle. And there's going to be a friction force pointed in that direction. Okay, and now what we need to do is we are going to use the work energy equation. And the problem does have the boxes starting at rest and the spring is unstretched. So if we do what we usually do, we look at the kinetic energy initial plus the work done on the system plus the kinetic energy final. Starting at rest, the energy is going to be 0. The final kinetic energy is going to be determined by when or where we talk about the system behaving. So it's going to be some function of velocity. We're going to have an unknown that we can play around with depending on the scenario. And then the work is what we need to calculate. And so when it comes to the work, the things that actually do work in this problem are, since the 5 kilogram block is moving horizontally, then that means that we have tension, friction, and the spring horizontal. But the tension is internal to the system because there's another tension in the other direction for the other block, so they cancel. And so we only care about the friction and the spring for the 5 kilogram block. And then for the 10 kilogram block, we have a weight at an angle. We have a friction that is moving in the direction. And we don't have, the normal force is not going to be pushing in the direction of motion. So we don't have to calculate the work for the normal force. And then, like we mentioned before, the tension is internal to the system. Okay, so those are our work calculations right there, those values that I have circled in green. Okay, so now what do we need to know? Well, in order to get the frictions, we need the normal forces because they give us the coefficients, but we don't know the normal force. So let's do a standard analysis of the system by doing the sum of the forces for the first block and the second block. So sum of the forces, we'll call the 5 kilogram block, block A. So sum of the forces of A in the y direction, they're going to be equal to the normal force of A and then the weight of A. So 5 times the 9.81. And there is not going to be any vertical acceleration. So we've got a 0. And that means that the normal force of A is going to be equal to 49.05 newtons. Okay, then we'll have the sum of the forces of B in the normal direction. So that's going to be equal to the normal of B, okay, minus the weight of B, so 10 times 9.81, and then cosine 50 degrees. Okay, there's not going to be an acceleration perpendicular to the ramp, so 0. And then that means that the normal force of B is equal to 63.06 newtons. All right, now we have the normal forces, which means now we can calculate the friction of A, which is going to be 0.2 times 49.05, and that is equal to 9.81. Okay, feels a little bit like a coincidence there, but no big deal. And then the friction of B is also going to be 0.2 times the normal of B, which is the 63.06 newtons. And that's going to be equal to 12.61 newtons. All right, now we used 0.2 because the boxes are sliding. We wanted the kinetic coefficient of friction. We are assuming sliding boxes for these friction forces at this stage of the problem. So now we can do calculations for the work on the different boxes. So we'll have our U, and we will have the integral of the distance traveled. So remember that I showed that there was this lowercase delta here is the symbol for our distance that we will be traveling, right? And technically, I feel like, okay, well, if this is equal, let me make this equal to the K. So 1,000 delta is the actual K value. So if we do the equation, we'll have negative Kx. Okay, and also we're going to have the friction force in this calculation. So we will do, because we don't know how far we're traveling, so we need the bounds of integration to be the distance. So we have to include the friction in here. So that's going to be the negative 9.81. That's the friction force of A. Okay, don't let that confuse you because of the coincidental number with the acceleration due to gravity. Okay, dx. So that's for the 5 kilogram block, or block A. And then for the block B, don't really have to do this. Well, yeah, you don't really have to separate them, but I'm going to. So now we're going to have the weight, but only the component of the weight. So this will be 10 times the 9.81, only the component of the weight that is in the parallel, in the direction of motion. So this is going to be sine 50 degrees, okay? And then minus, and they're going to have the friction for block B, or the 10 kilogram block, so 12.61. All right, and that's going to be basically dy. This calculates out to be, practice your algebra, 52.73 delta minus 500 delta squared. And this is joules. Okay, that is the function of the work as a function of distance. Now we can plug these values in to our work energy equation. So the U here is going to be the 52.73 delta minus 500 delta squared, and it's going to be equal to the 1/2, the mass being 5 kilograms, velocity squared, plus 1/2 the 10 kilogram mass velocity squared. All right, so this side, let's just simplify that. The velocity side simplifies to 7.5 v squared. All right, so now what we've done is we've set ourselves up to be able to solve most of parts A, B, and C. All right. So the first they ask us to find the maximum velocity of the blocks and the stretch in the spring in that position. So the maximum velocity is going to be when the change in velocity is 0. All right, meaning when the acceleration is 0. So if we take the derivative of the function, if we basically take this work energy function and we do the dv over d delta being equal to 0, then we will be able to find the maximum velocity. So that turns into 52.73 minus 1,000 delta, and then the other side is going to be 0. If we solve for delta, then we will end up with 0.053 meters. Now, if we plug that distance back into the equation, we can solve for velocity, and velocity will equal 0.431 meters per second. Okay, try it out. See if you get those numbers. Okay, so we found the position where the acceleration is now 0, which means the velocity is not changing. And we have to have a certain amount of knowledge. So we know that the blocks are going to start going downward, start from rest, start going downward. But eventually, we have to understand that since there's friction and there's weight and there's a spring, the spring will eventually match any forces that are causing acceleration downward and either stop the boxes or cause them to start going back up. Okay, meaning there's going to be some maximum velocity in the middle of that process. And so that process is going to cause acceleration downward, but then the acceleration will actually go to 0, and then maybe the acceleration will even start going up again, maybe. Or the boxes might get stuck at that location. So that's what we did there mathematically. I hope that makes sense. Okay, that is the answer for part A. This is the position and the maximum velocity of the system of blocks. Part B is asking for the maximum amount that the 10 kilogram block will slide down the inclined surface. Okay, well, that is going to happen when the velocity is 0. So is there a time where the velocity is 0? So basically, we just take this function again. Okay, but now we set v to 0. Pretty straightforward. Okay, so setting v to 0 will end up with an equation that is, sorry, this is getting a little cluttered, but I'm just going to write down here. It's just the 52.73 delta minus the 500 delta squared equal to 0, because velocity is 0. So the maximum distance is going to be 0.106 meters. Okay, again, part B. So this is part B. This is part A. Pretty straightforward. Part C, a little bit different of a concept here. So part C asks, determine if the blocks will rebound from the position of part B. Okay, they are asking us if when the blocks come to stop, will they continue by going back up, or will they actually slow down to a stop and then get stuck in that position? Now, that might not be obvious why the boxes would get stuck unless you're thinking about these two values right here. The kinetic coefficient of friction is 0.2. It's the friction when the boxes are moving. The static coefficient is 0.3. That is the coefficient of friction when the boxes are still. There's an instantaneous jump from one coefficient to the other. When there's any motion, the coefficient will be kinetic. And then instantaneously at the moment the boxes stop moving, there will be a jump up in the amount of friction to a coefficient of 0.3 instantaneously. So what we have to do is we have to see if this is a static condition. All right, so we got to tap into our CE 270 knowledge. We can basically do the sum of the forces of block A in the X, the sum of the forces in block A in the Y, the sum of the forces of block B tangentially, and the sum of the forces of block B in the normal direction, just like we would in CE 270. And we're going to set all of their mass acceleration values. So this is the mass acceleration of each one, all to 0, 0, 0, 0. And we're going to see if the numbers basically come to something where the friction will have hopped up to a value that is higher than what is needed to have a static condition. All right, so first, let's set this up and then I'll reiterate what I said. So the sum of the forces, I don't have the free body diagrams here, so go back and copy them if you didn't, or copy them right now. Pause the video and copy down the free body diagrams, and I'm going to just be writing the values on this next page here. So we've got our tension minus the friction force of A minus the 1,000 times, and our position is going to be the 0.106 distance that we calculated for the maximum displacement. So this was the value from part B. Okay, next we're going to have the normal force of A, and then minus the weight of the box. Okay, equal to 0 for the mass times acceleration. Okay, next is going to be the friction force of B minus the tension plus the mass times acceleration due to gravity, the weight, but only the sine 50-degree component, the tangential component. Okay, and then here we're going to have the normal force of B minus the weight, but only in the normal direction, so cosine 50 degrees, and that's also equal to 0. Okay, so we have basically 1, 2, 3, 4, 5 unknowns in 4 equations. But look at this. We can solve for the normal force of A, and we can solve for the normal force of B. Okay? Now, those values added together are going to be normal force of A plus the normal force of B is equal to 112.1 newtons. Okay? And then that also means that, solve for the numbers, and you'll see what I'm talking about. That also means that these equations here have the same term in them, the tension. So if you are to solve for one and the other, you will end up, and you know what the friction values need to be. You can set up a friction equation that is friction A plus B this is what's required, is 30.35 newtons. You can solve for these values, okay? And this is what I think is the most confusing part, is that this is what's needed for a static condition that we'd set up. We set up that there will be no more acceleration for all 4 of these particular directions for the entire system. So this is what is needed. All right, this is the needed friction. Now, how much do we have available? Well, if you just add up the frictions of A plus friction B, and you use the static coefficient times the total normal, okay, then we end up with, we actually have 33.63 newtons of friction, but we only need 30.35. This means we have more friction in the static scenario than what we need for equilibrium. So remember, just to recap one more time, this number is what is required to have a static condition. This number is what's actually available based on the normal forces calculated, the amount of friction that's actually there. And that friction for static is higher than what is required for a static condition. So therefore, these boxes will not slide after they have stopped.